Alright, welcome everybody. This is going to be our last video on atomic structure and quantum mechanics. So at this point, what I wanted to talk to you about was electron configurations. So up to now, we've gone through how, okay, the atom is this hard sphere. It has, then it has electrons in it. Then those electrons, they are outside a nucleus that's positively charged. Then we have the electrons in these orbits. That sort of paralleled the idea that light was quantized, and then we figured out that matter was quantized. Electrons can exist as these standing waves, and these standing waves occur within the atom, where the electron can occur in regions of space called an orbital. And so now we're at this situation where we have these electrons. Their positions are defined by the quantum mechanics and the quantum numbers that they are allowed to have, that they're assigned. And so now we need to really figure out, well, what are the electron configurations? So electrons, they will fill an atom in order of their energy. They will fill from the lowest energy, and then once that energy level is filled up, they will then occupy the next highest sub-level and energy level, and so on. And so this should look familiar to you. This is called the Pauli Principle. It also shows you what's known as the diagonal rule. It's the order of how the electrons fill up the atom. And so this is a nice diagram here. Normally I draw it out, but this one's already done for you. And so the first sub-level and energy level to fill up is 1s. Once 1s is occupied with 2 electrons, the repulsions become so great in that very small orbital that they're forced into the next largest orbital, which is 2s. Once 2s is completely filled, the next to fill up is 2p, followed by 3s. Once 3s is filled, 3p fills, and then what you'll notice is that instead of 3d filling, you actually have 4s fill first. So then you'll see that there is 4s filling next, then 3d, then we go back and fill in the rest of 4 and 4p. And then we skip again. We don't do 4d. Instead, we'll do 5s. And so this will continue. You should know this diagonal rule, but I'll also show you a trick using the periodic table that maybe you weren't ready for last year because you were just kind of using this. But the periodic table is actually really helpful with filling out electron configurations. So let's give this a try for some specific atoms. I'll do the first, couple of them with you. So hydrogen has 1 electron. So the first orbital to fill up is 1s, and so we'll have 1s, and we'll put a 1 there to show that there's 1 electron. Helium has 2 electrons. Both can fit into the 1s, so that'll have 2 electrons. Lithium is 1s, 2. Now that is completely filled. If we go back to the diagonal rule, the next one to fill up is 2s, and so now we'll have 2s with 1, that's 3 electrons. Boron, 1s2, 2s2, 2p, 1. Notice now the s is filled for 1s and 2s. Now we start filling up the p. For, wait, that's not right, I apologize. Beryllium is just 2s2. Got ahead of myself. Boron, though, is 1s2, 2s2, that's 4. Now we put 1, 2, and that makes it 2p1, that's 5 electrons. Carbon, 1s2, 2s2, 2p2, that's 6 electrons. Now p can occupy up to 6, so this one will be 2p3, this one will be 2p4, this one will be 2p5, and this one will be, neon will be 2p6. Once we get to sodium, then we'll have all of the previous, and now we'll go to 3s1. So now you could go through and fill out the rest of these. You should end over here with argon, argon being 1s2, 2s2, 2p6, 3s2, 3p6. If I did the next element in line here, it would be potassium. Potassium would be all of argon. In fact, you can write that as an abbreviation, all of argon, and then it goes 4s1. Notice it doesn't go 3d1. Once you fill up the 3p with 6, then you jump to the 4s and fill up that orbital first. Okay, so practice these. Make sure that you can do all of them. Now the other thing that we want to do is be able to do something called orbital diagrams. Remember, each of the sublevels has orbitals in it. S has 1 orbital, P has 3 orbitals. So if we start with boron here, boron will have 1s2, 2s2, 2p1. Now I could put this electron in any of these boxes. These boxes are called degenerate. So the 2p are degenerate. It means they have the same energy. But by convention, we start at the left and move right, just so that everybody doesn't go insane. So now I could do this with carbon. So if I do this with carbon, 1s2, 2s2, 2p, and now I have a choice. I have to put that second electron in. I'm going to put it next to it. This is called Hund's rule. And what Hund's rule says is that electrons will occupy individual orbitals before pairing with each other to minimize repulsions. So now I go ahead and I do nitrogen. Following Hund's rule, I'm going to have 3 electrons in separate orbitals. Now if I go ahead and I do oxygen, those electrons are going to have no choice. They're going to start to pair up, and we're going to have 1, 2, 3, 4. So now they're forced to pair up because they have the 3 unpaired electrons. Nitrogen's very special because these 3 unpaired electrons, they convey a very special stability because electron repulsion is minimized in that sense. Okay, you can do fluorine and neon to get an idea of what's going on with those. Now, the other rule that's followed is you'll notice that in each of these boxes, in each of these orbitals, I will put different spins. I will put an arrow going up and an arrow going down. And that has to do with the idea that no 2 electrons can have the same 4 quantum numbers. If we look here, if we make this 2p, that would make n for each of these electrons 2. If we do L, that would be p, so each one of these would be 1. If I did ML, each one of these electrons would be in the same orbital. This would be in this orbital, and this would be in this orbital. And if I did MS, these would have 1/2 and 1/2, 1/2 and 1/2. And so if you'll notice, these 2 electrons have the same spin, so they have the same 4 quantum numbers. That's not allowed. Pauli Exclusion Principle says that no 2 electrons can have the same 4 quantum numbers. Now, like I showed you on that other slide, you can also do something called the condensed formula. So this becomes really valuable for something like radon. You know, radon has 7 energy levels. That's a lot of energy levels. So you have this situation where you don't want to write out the whole thing. So when you do condensed gases, you use the nearest noble gas to represent the core electrons. This saves time and space. So if I did one that was kind of reasonable, like phosphorus, for example, that has 15 electrons. 1s2, 2s2, 2p6, 3s2, 3p3. If I wanted to abbreviate this one, I could take the core electrons. The nearest noble gas is this core, which is neon, and then I could just put on the valence electrons. So how can I use the periodic table to help me? The periodic table is actually really helpful. If we take, for example, phosphorus that we just did here, and let me just change the color so it's more visible. If I take phosphorus, so phosphorus is right here. It's in group 15. So this is 17, 16, 15. It's right here, and it's in P. This is phosphorus right there. So what the periodic table tells me the energy level based on the period. Energy level 1, energy level 2, energy level 3. But it's also organized by blocks. And so when I look at the periodic table, what I can see is that this is called the P block over here. And all the P blocks are aligned. So this group right here is P1. This is P2. This is P3, P4, P5, and then over here, P6. So if I take phosphorus, for example, I know its last electron, since it's in this group right here, I know its last electron is going to be p3. And so I know that phosphorus is going to be 3 because it's in period 3, P because it's in the P block, and 3 because it's in that column. Now this helps me a little bit because it allows me to really quickly go through and figure out, okay, where's my electron, what's the last electron. But instead of using the diagonal rule, I can use the periodic table. And I can go through and I can say, okay, well, 1s1, 1s2, 2s1, 2s2, 2p1, 2, 3, 4, 5, 2p6, 3s1, 3s2, 3p1, 2, 3, 4, 5, 6. I also have the D block here, and I have the F block here. So this is just to help to guide you. Now, the shapes of the orbitals, these are based on what's known as the azimuthal or secondary quantum number. You can see that the s orbital is a sphere. 1s is the smallest, 2s is larger, 3s is larger. You can graph probability of finding the electron and the distance from the nucleus. And you can see most of the electrons are really close. Just like we talked about in the previous video, there's a node here where you won't find an electron, and then here's my 1s over here, my 2s over here. Now you can also have p orbitals. P orbitals have these lobe shapes. And so each of the p orbitals, you have the 3 orbitals for p that we use as boxes, each one represents a py, a px, and a pz. If we go to d orbitals, there's 5 d orbitals here. 1, 2, 3, 4, and 5. And so each one of these has a different axis orientation based on its azimuthal quantum number. And you can see some of the d ones are really kind of funky. Okay, with energy filling, and when I look at the energy of orbitals, I like to compare them, and you can see between 1 and 2 there's this huge energy difference. But what is interesting is that when you get up higher here, and we look specifically at 4s and 3d, there's almost overlapping energy here. And this leads to some weird configurations that I'll show you in the next slide. Now, the last slide for this presentation, excited versus ground. If I take something simple like nitrogen, and I write out its electron configuration, I can make this an excited state. I can add energy to it, just like Bohr did when he, shot photons or excited the electrons in the hydrogen atom. And so I can make this something like 1s1, 2s2, 2p4. Or I can add a new level, 1s2, 2s2, 2p1, 3s1. These are excited. This is ground. So the last thing that I want to talk to you about is the weird electron configurations. Okay, so some of the weird configurations that you're going to see, the main ones that I want to talk to you about are copper and chromium. So copper should be 1s2, 2s2, 2p6, 3s2, 3p6. It should go 4s2, 3d, 3d9. And with chromium, if I copy and paste this, chromium should be almost the same, except at the end here, this should be 4s2, 3d 4. And it turns out both of those are incorrect. They actually go like this. Their last part of their configuration is 4s1, 3d10 for copper, and 4s1, 3d5 for chromium. And just to really quickly explain one of them, if you look at chromium, if we draw out the electron configurations for them, 4s, and then we put 3d, when we do it 4s1 and we put 1 electron here and 3d5, we put our 5 electrons here, the electrons are repelling each other less. And that is because now they're spread out over individual orbitals. Spreading them out over individual orbitals is kind of like an extension of Hund's rule, except now we're doing it across 2 levels. We're doing it across 4s and 3d. This minimizes the repulsion. This increases the stability. Now there are other elements in the D block that do this, and you don't need to know them. For the SAT subject test and also for the IB exam, they expect you to know copper and chromium though. Alright, thanks so much for watching. That's the end of quantum mechanics. I hope you have a great day, and I'll see you soon.